Hello friends, in this video we are going to discuss about waves in plasma. First we discuss about representation of waves. Any periodic motion of a fluid can be decomposed by Fourier analysis into a superposition of sinusoidal oscillation with different frequencies omega and different wavelength lambda. A simple wave is any one of these components. When the oscillation amplitude is very small, the waveform is generally sinusoidal and there is only one component. When we talk about any plane progressive wave, we can represent that wave with the help of an equation. Any sinusoidal oscillating quantity wave having density n can be represented by n is equal to n0 exponential of I kr minus omega t, where n0 is the equilibrium density, such as k is the propagation vector, and that can be resolved in 3 dimensions as vector k is equal to I cap kx plus j cap ky plus k cap kz, and r can be represented as, which is the position vector. Vector r is I cap x plus j cap y plus k cap z. Then we have k dot r, vector k dot r is equal to k x cap plus y ky plus z kz. Let's take this equation number 2, where n0 is the constant defining amplitude and k is the propagation vector, and if the wave propagate in x direction, k has only the x component, then the equation become n is equal to n0 e raised to the power I kx minus omega t. Now we will take the differential of equation number 3 with respect to time and position coordinate, where omega is the angular frequency. Let differentiate in the equation with respect to time. d by dt n is equal to minus I omega n0 e raised to the power I kx minus omega t. After differentiating, we get dn by dt is equal to minus I omega n. Let's take this equation number 4 and differentiating the equation number 3 again with respect to the x. We get dn by dx is equal to I kx n0 e raised to the power I kx minus omega t. Here n0 e raised to the power I kx minus omega t we can substitute with by n, and then the equation we get dn by dx is equal to I kx n. Let's take this equation number 5. This implies that d by dt can be replaced by minus I omega. You can see d by dt we can replace with minus I omega, and the d by dx can be replaced by I kx. Then the value of del, we get del is equal to I k and delta n is equal to I k n. Let's take this equation number 6. The real part of the expression is to be taken as the measurable quantity. As we know, e raised to the power I theta is equal to cos theta plus I sin theta. Here we have two parts, real parts plus imaginary part. Here we will take only the real parts. Hence the real part of n we can write n0 cos kx minus omega t. Let's take this equation number 7. Here kx minus omega t is the phase of the wave. Because the wave is moving with constant phase, then the rate of change of phase should be equal to 0. Then we can write d by dt kx minus omega t should be equal to 0. After that k dx by dt minus omega should be 0. Then dx by dt is equal to omega by k, which is equal to the v phi. The v phi is known as the phase velocity. Basically it is a velocity of a wave which is moving with constant phase. If omega by k is positive, the wave moves in right, and omega by k is negative, then wave move in left. X and t are in directly proportional. As x increase, t increase, x decrease, t decrease. Now let us discuss about group velocity. The phase velocity of a wave is that tells us what is the velocity of the point of a constant phase on any wave. The phase velocity of a wave in a plasma often exceeds the velocity of light, which is c. This does not violate the theory of relativity, because an infinitely long wave train consist amplitude cannot carry any information. The carrier of the radio wave, for an instant the carrier have no information until it is modulated. The modulation information does not travel at the phase velocity but at the group velocity, which is always less than c. To illustrate this, We may consider a modulated wave formed by adding two waves having nearly equal frequency. Let E1 is equal to E0 cos k plus delta kx minus omega plus delta omega t. Second wave is E2 is equal to E0 cos k minus delta kx minus omega minus delta omega t. E1 and E2 different in frequencies by 2 delta omega, since each wave must have the phase velocity omega by k appropriately in the medium which they are propagating. For the each we can write a plus delta k is equal to a and delta kx minus delta omega t with the help of b. And now we have to substitute the value of a and b in the equation for the e's, and the resultant wave we can achieve by adding the E1 and E2. By adding E1 E2 we get E0 cos a plus b plus E0 cos a minus b. With the help of formula we get cos a plus b is equal to cos a cos b minus sin a sin b. The value of cos a minus b is equal to the cos a cos b plus sin a sin b. Then the resultant equation E is equal to E1 plus E2 becomes 2E0 cos a cos b after the cancellation of the terms which are cancelling. Then the resultant equation E becomes E1 plus E2 is equal to 2E0 cos delta kx minus delta omega t cos kx minus omega t. Here we have substituted the value of a and b. As we have earlier assumed, a is kx minus omega t, b is delta kx minus delta omega t. And the resultant of the wave can be shown in the figure, where Vg is group velocity and V5 is the phase velocity. This is the simultaneously modulated wave. The envelope of the wave given by cos delta kx minus delta omega t. This is what the carries information. It travels with the velocity of del omega by del k, which is the phase velocity. Taking the limit delta omega tends to 0, we get the group velocity Vg is equal to del omega by del t. And this is the quantity which cannot be exceed the limit of c. C is the speed of light. Now let's take a review what we have done. We have a wave equation n is equal to n0 e raised to the power I kx minus omega t. We have differentiated this equation with respect to time and position. Thereafter we get the value of delta n which is equal to ikn and the value of delta which is equal to ik. Thereafter we have applied the condition for constant phase in the equation. For this the value kx minus omega t should be 0, means the rate of change should be 0 for the condition of constant phase. After differentiating we get k dx by dt minus omega is equal to 0. Then the value we get dx by dt is equal to omega by k, which is the phase velocity. Now for the group velocity we have taken two wave equations E1 and E2 nearly about same frequency. E1 is equal to E0 cos k plus x minus omega plus delta omega t. E2 is equal to E0 cos k minus delta k x minus omega minus delta omega t. After that we have calculated the resultant of these waves. E resultant is equal to E1 plus E2. E resultant is equal to E1 plus E2, we get 2E0 cos A cos B. Thereafter the value we get in this equation, the first term cos delta kx minus delta omega t represent the group velocity and the another term represent the phase velocity. Then we get Vg is equal to del omega by del k, which is the group velocity.